All right, so we're going to look at what's known as hypothesis testings today. Nothing is actually going to really change from what we've already done. I'm just going to be adding a step at the end. I will tell you that one of the things that is going to change on the test, however, for this test, because a lot of the questions are basically a true or false type answer, you're going to have to show all your work for the test. So I will be collecting all the work for this test next week. So, and if you do not have the work, even if you get the answer correct, you will not get credit for that answer. Okay. So do follow along with how I'm showing you how to do the workout and actually make the call on it. All right, just like in science class, a hypothesis is the statement or a claim that you are making. So in this case, it's a statement or claim about the characteristics of one or more of the populations. So this is what you believe to be true or what you're trying to test to see if it's true. The hypothesis test is a procedure based on sample evidence that's used to test a statement or claim about the characteristics of one or more of the populations. So if we want to make the claim that 60% of people in the United States like vanilla ice cream, that's my hypothesis. I would then collect some data on it, do a statistical analysis on it, and based on that, determine if my claim could possibly be true. Okay, that's my hypothesis, and then what we would go through and doing the testing for. The first of the big things that we're going to need to use. You have two properties that you're going to start with. The first one is your null hypothesis. This is a statement about the value of the population parameter. This is your null hypothesis will always be equal to. Okay, so your null hypothesis will always be equal to. It's an H with a little O underneath it. Or it's supposed to be like a 0, so it's H naught. Okay, and the big piece of this one is it's always the equal. Now, it could be the mean equals or the proportion equals, depending on what type of problem we're doing. We're going to do mean today, and proportion we're going to do on Wednesday. The alternate hypothesis, which is with an A or an H with a little A underneath it for alternate, is the statement or claim that we're trying to find evidence to support. So somehow we're going to say that it's different than what the data that I got. It's either going to be greater than, less than, or not equal to. So your null hypothesis is always equal to. Your alternate hypothesis is always either greater than, less than, or not equal to. It'll never be greater than or equal to or less than or equal to. It's basically supposed to be the opposite of what your null hypothesis is going to be. Okay. This is in essence the one piece we're adding. All right, let's do a couple of these so you can actually see what this means. Suppose a potato chip manufacturer is concerned that the bagging equipment is not functioning properly when filling up a 10-ounce bag. He wants to test a hypothesis that will help him determine if there's a problem with the bagging equipment. So, the null hypothesis is what should be happening. So what should be happening? Yes. Correct. So that means my null hypothesis is my mean equals 10. That would be my null hypothesis. We want to test the claim that the bagging equipment, if there's a problem with the bagging equipment. what would be, if there was something wrong with the bagging equipment, what would happen? Okay, so we have three options: less than, greater than, or not equal to. So which one of those three? If it could be either or, that means it's just not going to be 10. So my null hypothesis, or my alternate hypothesis, is the mean does not equal 10. Because that means it can go either direction. If it's filling up the bags too much or too little, both of those would be a problem. Does that part make sense? We're going to do a couple more of these before we actually go into the actual, like, all of the steps. But these two statements is going to give us the information that we're going to use to go forward in the actual test. Martha Brandon wants to assess her candidacy in a forthcoming race for the state senate. She is an incumbent and wants to raise sufficient support to retain her seat. How would she formulate an appropriate hypothesis to determine if there's an overwhelming evidence that she will retain her seat? So what would be the null hypothesis in this case? There's no numbers in it. So we have to use, remember, the null hypothesis is what it equals. Yes. It's always got to be a number. What do we typically use when we're looking at races? You know, it's a what? We typically use a percent, right? What's that percent? That would be, yes. Right. So perfect. So this is actually a very important thing. You might want to say that the null hypothesis is greater than 50%. But the null hypothesis has to be equal. So in this case, my null hypothesis is 50%, or 0.5. My alternate hypothesis, what I want to test, is that I have greater than that I will retain my seat. So for my alternate, I'm going to be greater than the 0.5. I will tell you, that's the hardest thing. You're going to want to change the null hypothesis to something other than equals. Yes. I'm confused by 0.5. Wouldn't it be like 0.51? Well, technically, it'd be 50% plus one vote. So we can't say 51% because we don't know how much that one vote is. So when we're looking at this, we set the middle, my mean, as 50% because that would be a 50-50 split. Where I'm testing my alternate hypothesis, I want to say it's going to be greater than that. And that's why I'm saying greater. If I put 0.51 there, I'd have to say greater than 51 on the bottom piece because those numbers will always be the same. Okay? So the null hypothesis and the alternate hypothesis will always use the exact same number. One's going to be equals, and then the other one's going to be less than, greater than, or not equals. But the null hypothesis always equals. Yes?
What made it bigger than?
Because she wants to determine if there's overwhelming evidence that she will retain her seat, which means she would need more than 50% of the vote. Most situations, they're going to give you some numbers in the problem. I like this problem specifically for the reason that it tricks you into thinking the null hypothesis is greater than and not equal to. So. All right. Mr. Russell, or Ms. Russell, the head product tester at Hathaway Tool Company, is assessing a new design for a series of bar hooks. The hooks have been designed to give way if it gets too hot. The previous design gave way at 240 degrees. They want to develop a test if the newly designed hooks give way at a higher temperature than the previous design. So what is my null hypothesis? What is the status quo? 240. So my null hypothesis is that the mean equals 240. What would be my alternate hypothesis in this situation? Greater than 240, because it says gives way to a higher temperature. Yes.
Do we put the units in?
You can, you don't necessarily have to. Because all the actual tests and stuff that we're going to do in a minute, it's not going to really use it. All right. Let's do the problem and then I will explain the bottom piece to it. So the average national reading level for high school sophomores is 150 words per minute with a standard deviation of 15. Local high school board member wants to know if sophomore students at Lincoln High School read at a level different from the national average for 10th graders. The level for the test to be set at 0.05 and a random sample size of 100 10th graders has been drawn and the resulting average is 154 words per minute. This is typically what you're going to see for a problem. They're going to give you a lot of other information and stuff there. We're going to need all that information. None of this information is just extraneous, but whatever that word would be. But the very first part of this problem, we might not need at all. So what is the null hypothesis for this problem? Again, what's the status quo? Yeah. Right. That's the national average for the school or for the sophomores. Yes. No. It's just 150 words per minute. Your null hypothesis, your hypothesis, or an alternate hypothesis will always either be mean or proportion, depending on the problem. In this situation, we're going to be using mean. On Wednesday, we'll do the proportion problems. They will never be standard deviation. We're not going to do those problems. Go to steps 2, you'll do the standard deviations problems. It's a whole nother table and a lot more work. All right, what's the alternate hypothesis for this situation? What am I trying to test? So this is where the English comes into play. What words in it tells me what I want to figure out. Yeah.
They just said if they want to know if the reading level is different from the national average,
Okay.
So it'd be not equal, right?
It'd be not equal to. So this is another one that's can be very tricky. Because you're going, oh, it's 154 words per minute that they're reading at. So it's obviously greater than. Don't let the other information change your view of what they're trying to test. Okay? Because that can change what your outcome is going to end up being in the end. So they wanted, all they're testing for is if they read it at a level different from. That would be not equal to. If they say they want to read it at a level greater than, that'd be greater than or less than, things like that. All right, you are going to need your t-table. We are using the t-table, but we're actually going to be using the z's down the bottom for this problem. But it's all on this table, so it makes it nice and easy to use. And this would be why, yes.
That one of the z values is different by like 0.01.
Yeah, it's it should not matter. None of these answers are going to be so close that that's going to make a difference. All right. So at the very top of the t-table, you see where it says cumulative probability. Then it says one-tailed and two-tails. And I told you that last class we were only looking at two-tails and not to cross off the one-tails. Hopefully you did not, because we're going to be looking at those today. When we're looking at the hypothesis testing, when we're looking at the alternate hypothesis, depending on the direction or the symbol that's used, depends on the number of tails we have. Not equal to is two-tailed because we are looking in both directions on the graph. Okay? Less than or greater than is one-tailed because we are only going to be looking in one direction on the graph. So if we're looking for greater than, it's called the right tail because we're looking at the right side of the graph. If it's less than, we're looking left tail, it's the left side of the graph. Okay. So not equal to is two-tailed. Less than or greater than or less than is one-tailed. So for this problem, is it one-tailed or two-tailed? It is two-tailed. Does everybody understand why it's two-tailed? That will make a big difference. Okay? Because depending on where you're putting the percentages, that can make a change in what you're looking at. All right. Oh, yeah. Got it?
Yeah, the table just didn't flow down.
Oh. The two tables? I do. I do have a few of those lots. No problem. We're going to go back to that in a second. So let me do it this way. So let's pull the information out of this problem so we can start to get some information about it. What is the mean in this problem? The 150. The nice thing is it'll always be your LHAP. So my mean is 150. What's the standard deviation? 15. Now, we need to look at two different possibilities, right? Because we have two different types of graph or two different types of tables. Is that the population standard deviation or the sample standard deviation? It doesn't say population, but it's given to you in that same sentence. Okay, it was the national reading level is 150 words per minute with a standard deviation of 15. So it's all in that same sentence, so it's the population standard deviation. If they told us that after they talked about the 154, then it would be the sample. In this case, it is a population standard deviation, and it is 15. What's the value that I'm testing? What's the value of my sample that I got?
Like, what does it come out at?
Yeah, what information did they give us? They told me the average was
That they received was one.
right 154. So that's going to be my X value. Is the 154, and we tested 100 students. Okay. The last piece of information we need to know is what is our significance levels going to be. So they said the level of the test is set to be 0.05. Okay, so that is my significance level. All right, so let's look at our T-table. So we are using a one-tailed or two-tailed test. This was a two-tailed test. So at the very top, you're looking at two tails. And we're going over till we see the 0.05. Okay. So we're looking at that one right there. So we're looking at two tails because it's not equal to, so it's both directions. And we're doing the 0.05. That was the information they gave us. Since this is a z-test, because it's the population one, go all the way to the bottom and get your z number, which is 1.96. Okay? Everybody understand how we got that number? Because that's one of the two very important numbers you need. So it's two tails because it's not equal to. Significance level 0.05. And it's a z-test because we have our population standard deviation. So we go down to z and it's 1.96. Yes.
How do you rate the significance level, or is it just written out?
I literally just put sig level 0.05.
Okay.
Yeah, that's all I do is that. All right. Go back to our wonderful little bell curve. Since it is two-tailed, we have the 1.96 on both sides. We have the positive of it and the negative of it. Remember, it's symmetrical, so it's the same on both sides. Okay. We shade the outside edges. So anything outside of that, we're rejecting our null hypothesis. You'll understand what that means in a second. If it's inside, we fail to reject the null hypothesis. Is anywhere on there say, I accept the null hypothesis? No. Anywhere on there say, I accept the alternate hypothesis? No. You never actually accept anything. Okay? You're either going to fail to reject the null hypothesis or reject the null hypothesis. We're never going to make the claim that the information that I got is the exact answer. All we know is it's going to differ from the null hypothesis. Okay? In some way or form. But just because the information I have is there does not mean that that's the actual final answer. So we are going to either fail to reject or reject. Okay? I know, it seems like a lot. Once we start going through a couple of these problems, you'll see how it's not as much as it sounds.
Center part with the fail?
Yes, the center is the fail to reject. Outside edges is the reject. All right. What was the number that we've always been using to, in all the rest of the problems so far? We were doing the confidence interval, we were doing everything else. We were always looking for our what? We were looking for our z-score, right? Let's find our z-score for this data. Okay. Yes.
Did it already give us it? Because-
No. That's where there's two numbers. That's where we're looking to test. We want our z number for 154. I haven't used 154 at all yet. So that's where we're going to get our z to be able to compare. The formula has not changed. It's the same formula we did before. X minus the mean over standard deviation divided by the square root of n. So it's 154 minus 150 over 15 divided by the square root of 100. And I probably should have typed that into Desmos before just now. So we type that all into Desmos. And my z-score is 2.67. Remember, your z-score is always 2 decimal places. Okay? Last step. Where is 2.67 on this graph? Somewhere over here, right? That's 2.67. Oh. Oh, that's I'm like, wait, I know I supposed to type over. That's where the 2.67 is. Where is it on my graph? Reject. Okay. So, the final ruling. We're rejecting the null hypothesis. What was the question that this person was asking originally? What were they trying to find with this data? Okay. We've rejected the null hypothesis, so we can say that there's significant statistical evidence that the high school reads at a different level than the national mean. Okay? I'm going to type this because I know I'm going to. Yeah, or significant statistical. Really? All right, it's not going to leave. That's right. I did not say the high school reads at a higher level than the national mean, because that's not what we tested for. Okay. They could have, with the exact same information that they just gave me, asked that question, and we would have been able to say that. Okay. But that wasn't the question they asked, and that's not the question we tested for. We tested for different. We tested for both directions. So that's why we have to say different, even though the data shows that it was higher. Does that make sense? Yes.
So, for example, if it was just like, did they test higher? Like, if that's what they were asking, would we say, like, how would we phrase that? I guess.
Well, first of all, we would have done it different. We would have used a one-tail test instead of a two-tail
So
test.
you would have found a 0.05 and a one-tail line?
Correct, which would have changed these numbers here.
Right.
Okay. But if that was, we did all that, it still would have been over there because the 2.67 would not have changed.
Okay.
We would have said that there is statistical evidence that the high school reads at a higher level than the national mean in that situation. We're done with this problem. We're not done for the class, but we're done with this problem. I'm going to do a few more of these. I know there's a lot of little steps. Okay. Yes. Yeah, because basically your option is fail to reject or reject. So the majority of the questions on the homework in this section, that's all they're going to ask. So it's like, I can't give you I need to see how you figured that out. No, so all we can say is that there's statistical evidence that says it is different than. I cannot say that it is true because you could come up with another study tomorrow and it's not true. Like that's possible. So all I can say is based on my statistical data is that there's evidence that it shows that it's better than that. That's higher than that. This is why a lot of mathematicians hate statistics, because it is the only form of math where when you finally come up with an answer, it might not be true always. Okay, it is literally the science of math. Like in science, you do an experiment, there might be 5 of you in the class doing an experiment, yours might work and the others don't. That's possible. So you go, okay, well, did I do something wrong, or did it just, that's the way science works. You do enough experiments, then you can start to say, well, maybe this is the way it always happens. But even then, somebody can come up and say, no, this isn't true. So that's where statistics falls into that more scientific field than a normal math, typical math class.
So if it did land in the fail to reject,
We're going to do one.
would that, like, if we're just using the cross as an example?
You would say there is not enough statistical, you would say there's not enough statistical evidence to say the high school reads at a different level than the national.
Okay.
At that point. All right, let's do another one. I won't be switching screens for this one. It's all going to be on one screen. Okay. So the first thing you're always going to want to do for these problems, find the null hypothesis, find the alternate hypothesis. That is always step one. So what's the null hypothesis? 16,000. I mean, equals 16,000. I'm missing that on this one. I gotta find it. What's my alternate hypothesis? Let's say increases. So we're looking for greater than. All right. The next thing that I typically do is I will find my significance level and mark up my graph. That's the next thing I do. So what is my significance level for this problem? 0.01. All right, one-tailed or two-tailed? One-tailed. Okay, so look at your graph, your t-table. We're going to look at one-tailed, 0.01. So we're at this point right there. And what is my, we have the, this one gave me, says assume the standard deviation is the same. So we're going to use the population standard deviation for this one. So what's the 0.01 on the one-tailed for the Z? .326. So now when I mark up my graph, the 2.326 is here. My shaded region is only that part right there. Okay, so that's the reject. Okay. Does that part make sense? Everybody with me to there? Okay. Now, let's find our z-score for the data. I've got to give you some of these numbers because they didn't put them all in this. It was a separate section of the problem. All right, so my mean is the 16,000. My standard deviation is 2,500. The new test is 16,200 hours. And we're testing 1,000 chips. So you can find our z-score from there. All right, so my z is what? 2.53. So we are over here somewhere. So we reject. The null hypothesis. And we would say that there is statistical evidence to show that the new process increases the life of the chip. Okay. Because it's a separate part of the problem, I just gave it to you. It was one of those problems I did in like 3 different steps in the book, and I forgot to copy the line where that was, so I just gave it to you. Normally, it would be given to you. Yes.
So you said the answer is that there's statistical evidence that the chip increases.
The new process increases the life of the chip. Yes. Now, this is one of those ones. Look at the if you messed this up and did 2 tails, what's the z-score for 2 tails for 0.01? 2.576. And you'd have been in the failed to reject region. Okay. This is why it's important to make sure you're picking the right one. Okay, because if you don't, you could be off. And that's also the reason why showing your work is extremely important. Because, for example, in that problem, if you put failed to reject, it's wrong. However, giving me all your work when I'm going through and looking at it, if that was the only mistake you made, you get points for it. Okay. Because if you showed me your null hypothesis, your alternate hypothesis, all that stuff was correct, but you picked two tails instead of one tailed, yes, that's a major mistake, but it's not a zero mistake. Okay. All right. Okay. Find me my null hypothesis, alternate hypothesis, significance level, and the z-score part for that. The word differs means not equal to. Told you, the killer on this class is going to be the English. It still is.
Why is it 35 and not 29?
Because the sample's 29. She believes that the time will take 35 minutes. They did the sample and it was 29 minutes.
Does it matter if this is like mean time?
No, it's still mean. It's still average. You're never going to use your experiment for your hypothesis because you don't do that until after you made your hypothesis. Okay, think about it just like a science class. You make your hypothesis, then you test it. Same concept here. The difference is they're giving it all to you because they don't want you to make you go out and do it. Although it's funny. So, and I don't know if it was for a stats class or psychology class or anything else. I was over getting a soda out of the machine over there the other day, and this girl walked up to, there was two of us standing there and said, "Are you a student?" And she was asking questions of students. And I didn't get a chance. I told her I wasn't a student because I had to go to class, but it was like I didn't get a chance to ask her what class she was doing it for. So what kind of study was she doing? Was it? We would call that a what? Yeah, convenience sample. She was sitting in the lobby over there just asking people she saw. That's convenient. Okay, sorry, totally different topic, but it just popped into my head. All right, so we've got that. What's the significance level? Is 0.05. One-tailed or two-tailed? Two-tailed. Population or sample mean, or sample population or sample standard deviation? We have the sample standard deviation. So we need to use T, not the Z. So my N is 20, so my degrees of freedom is what? 19. So we're looking at our T table, and we're using the T this time. So 0.05 for two-tailed. So there. And we're going to go down to 19. So 2.093. And since it's two-tailed, it's on both sides. We know this is the sample standard deviation because it's in the sentence with the samples. And they even use the S instead of the little funky omega symbol. All right. Now, find me my t-score for the data. Yes. It's the same equation you just used for Z. The degrees of freedom is always one less than the sample size. So degrees of freedom is n minus 1. Yeah, the whenever we're looking at mean, that formula doesn't change. When we get into the proportion one is where that formula changes a little bit, which is why I'm going to do that one separately. So what did we get for our T? Negative 3.35. So we're down here. So we reject. So there's significant evidence to conclude that the completion of the new test differs from its intended duration. I swear I have one in here that fails. Is it starting to make a little more sense now that we're doing more of them? A little more sense? It's a lot of steps. It honestly is. I'm not saying it's not. It's most of it, like all this, except for that, was what we did before. That doesn't change. So you're always going to be doing that. That's always part of that experiment that you're doing. That's the data that you're collecting and to being able to analyze it. What you're trying to do here is the data that you collected so far different from what your norm is or what you believe it to be that the original premise couldn't be true. Okay. So like we did a problem the other day with Pepsi and Coke. And we're like, okay, a 50-50 split. But then we found like 40% of the people only like Coke or Pepsi when we did our experiment. That's a significant difference from the 50-50. So our initial conclusion of that it's split 50-50 probably wasn't true. So we make those changes. That's what this is. It takes the we believe this to be different and gives us a numerical way to test it. Okay? Because we're comparing it to that significance level. All right, set up my problem. Yes.
Oh, never mind, sorry. I just.
Okay. Yeah. Oh, it doesn't. Hold on. 0.01. Are we using T or Z?
Z because it's over 30.
It's Z because it's the standard deviation is for the population.
Audience population.
Huh? It says historically the average claim size is 24,000 with the standard deviation of 2,400. That's talking about the population. So it's Z.
I guess it's always looking for the word.
Oh.
Mm-hmm.
You're not always going to get the, the word population.
I'm not right saying that Z is if it's over 30.
Yeah. So like in this case,
Can I
yes.
figure it out from that though, right?
Yeah, you should be able, in most situations, that is also true. All right. So One-tailed or two-tailed? One. So 0.01, so we're using 2.326. So then we have find your Z. Yes.
I got a strange difference in that,
What'd you get?
I got a three.
Yep.
I mean, 3.7.
Yeah.
It was so far off that I was
I know.
like scared.
Hurricane Andrew was probably before most of your time. Destroyed southern Florida in 1992. But at the time, it was the literally most destructive hurricane to ever hit the United States in terms of monetary value. So, but it goes to show how it's way out there. So yes, the claims are definitely greater than the historical average. There's definitely significant evidence to show that. So we would reject the null hypothesis of the situation. But that's actually why, like, insurance companies use this data a lot. After Hurricane Andrew, that new data got rolled into their historical average and increased it quite a bit. So that then goes through and increases your premiums, increases all this other stuff. So that's how, like, you see the forest fires out in California and everything else, and they're starting to drop because, again, the claims are going to be so much higher than they expected. Same thing happened in North Carolina with the floods. So it happens. So yes, that number is way out there. So, and if we think about it, just looking at what's 2,400 plus or 24,000 plus 2,400 is 26,400. You're already at like one standard deviation out. This 2,700 claims is almost two standard deviations away from it to begin with. So you're starting to get into that realm of it's probably not going to happen. So.
Do you know if you're using the D or Z again?
Depends on where the data is. So this one, we use T. It says she randomly samples 20 employees, finds the mean time to take 29 minutes with a standard deviation of 8 minutes. That 8 minutes isn't all within that sample that they've done. That's T. This one, historically, the average claim size was 24,000 with a standard deviation of 2,400, and then it starts talking about the randomly thing. That is populations, we use the Z. So you just have to figure out if population or sample. That's the piece that changes that. So all the rest of the stuff, like the calculations and everything else, is the same. The only thing that impacts is that number, how you find that number. So. Let's do this one. Significance level 0.05. Wrong one. This one. Yes.
I just had a question about the problem with like 2 back where our N was 20. How- did you say like it has to be above 30 for it to be a normal curve?
No, anything can be a normal curve. Once you're above 30, you can assume a normal curve.
Oh, but because this one specifically states.
Yes.
Okay, got it.
It's not clear at the start.
Yeah, like in this one, he says, well, it was 84, so it has to be Z. So, yeah, typically if you're going to use
That's not
T,
good off the book, you know what I mean?
yeah, typically if you're going to use T, it's going to be a lower number. I keep falling down. The IRS one I know is a fail, or is a reject one. I think the last one's not. So we'll do that one. All right. So what do we got? What's my null hypothesis? What's the population mean? 4575. They gave it to you out of order in this situation. Yes.
But it doesn't equal, so they just want to know if it's greater, not if it's greater.
Yeah, it says diet affects the height. It doesn't say greater or lower. So this would be not equal to. So two-tailed 0.05. This is a T. So my degrees of freedom is going to be 11. So 2.201. You too. So it's T for this one.
Negative 2.96.
Negative 2.96. So we're down here and we're rejecting again. They're not all rejecting, I swear. Let me just do this number real quick and then I'll show you. I think I'm going to do this. 11, 6, 4, more than 90. And we're testing 200. Yeah, this was. All right. So my significance level 0.01. All right, so now this one. My null hypothesis is 1190. My alternate hypothesis, if the label's accurate, so it's not equal to 1190. And are we using T or Z for this one? Technically, this one's T because it's a sample. The sample has an average with a sample standard deviation, so it's T. There's 200 packages, so it's going to be up there, but it is technically T. One-tailed or two-tailed? Two-tailed, so we're going to use 2.626. That's the 100 on the. Now, this is where if you used the 2.575, which would have been the Z, it is not going to make that big of a difference in this situation. One significance level, two tails. So my mean is 1190. X bar was 1167.34. My standard deviation is 252.94. And my N was 200. So my T, when I did the calculation, comes out to be negative 1.27. So that is right in here. So we fail to reject.
So you went to 100?
Yeah.
Even though it's 200?
Because there's not 200 on it. So it's closer to 100 than 1,000.
Would the answer be right for Z square?
Yeah.
Yeah.
Because again, what was my T? So even if you would use the 2.576, it's not going to change that. It's still going to be fails to reject. You're not going to have a number that's going to be so close that that is going to make the difference. You could if it was under 30, because those numbers get quite a bit different. But when you're up in that number high, it's not going to make that big of a difference, and your number is not going to be that close. So in this case, they picked it up, and we're failing to reject the null hypothesis. So there is not significant evidence to claim the label is, or there's not significant evidence to claim it is different than what the label states. I cannot claim the label is correct. I'm just saying that it is not, there's not enough statistical evidence to claim that. That's failing to reject. I knew I had one on here that was fails to reject. All right. Wednesday's class, the only difference is we're looking at proportion problems. But we're still going to be doing basically all the rest of the stuff. The null hypothesis, alternate hypothesis. For this is next Wednesday. And then we have 2 review days for the final, and then the final on the 12th.
So what's next week?
Next week, Monday's review, Wednesday's test for chapters 9 through 11. Then I have a week for review for the final. And then the final's the 12th.
I know, is the chapter review up? Did it work on the study?
It should be. If it's not, it will be there tonight.
Okay.
I'll check when I'll check now while I'm sitting here. Oh, shoot. Don't remember.